What is a transformer architecture? It all began with a problem. Machines could read, but they couldn't really understand. Sentences were just strings of words, and long-range meaning got lost in translation. Then, in 2017, something revolutionary happened. A new kind of architecture stepped onto the stage, not just faster or bigger, but smarter. It didn't read words one by one. It saw the whole picture at once. This was the birth of the transformer, the model that turned artificial intelligence from clever to conversational. Today's most powerful language models, from ChatGPT to Bert, whisper its blueprint. But what exactly is a transformer? And why did it change everything? Transformers were a significant advancement in developing neural sequence models and opened the door to universal language understanding and generation. They form the basis of most modern pre-trained models in natural language processing, NLP. Before transformers, models often process sequences of text one word at a time, making it difficult to capture long-range dependencies or understand how words far apart in a sentence related to each other. Transformers changed this by introducing a mechanism that allows the model to consider the entire input sequence simultaneously. The core idea behind the transformer is its self-attention mechanism. Imagine reading a sentence and needing to understand the meaning of a particular word. You would likely look at the other words in the sentence to figure out the context. The self-attention mechanism does something similar for the model. For each word in the input, it calculates how much attention, or weight, it should pay to every other word in the same sequence. This allows the model to identify which words are most relevant to understanding a specific word or generating the next one. A transformer model is typically composed of a stack of identical layers. Each layer usually contains two main parts, a self-attention mechanism and a feed-forward network, FFN. The self-attention part allows the model to create rich representations of each word, taking into account its relationship with all other words in the input. The FFN is a standard neural network that processes these representations independently for each word, adding further transformation and complexity. By stacking many layers, the model can build increasingly sophisticated understandings of the text. There are different variations of the transformer architecture used in pre-training models. Encoder-only models. These are primarily used for understanding or encoding input sequences. Models like Bert use this architecture and are good for tasks like text classification or analyzing relationships between sentences. In an encoder, each word can attend to all other words in the input sequence. Decoder-only models. These are the models most commonly referred to as generative LLMs today. They are designed for generating sequences, predicting one token after the previous ones. In a decoder, each word can only attend to the words that came before it in the sequence, simulating the process of generating text from left to right. This unidirectional attention is crucial for the auto-regressive generation process. Encoder-decoder models. These architectures have both an encoder and a decoder working together. The encoder processes the input sequence, and the decoder generates the output sequence based on the encoder's understanding. These are often used for tasks like machine translation or summarization, where the output sequence is derived from an input sequence. For generative LLMs, the decoder-only transformer is the predominant architecture. These models take an input sequence of tokens, represent them as numerical vectors called embeddings, which we'll discuss later, and process these embeddings through many layers of self-attention and FFNs. The output of the final layer is then used to predict the probability distribution for the next token in the sequence. The transformer architecture, particularly the decoder-only variant, provides a powerful way for large language models to process and generate text by efficiently handling relationships between words across entire sequences, enabling the remarkable language capabilities we see today.